Okay, everyone, it's Friday, and Friday before spring break, meaning that none of you are watching this right now. Okay, that's why we film this stuff, and we also have an extra hour today, and it's been a while since we had an extra hour since we had that exam. What I'm going to do is I've got a couple of example problems. Definitely I will ask a question on the exam that will be very similar to one of the example problems I'll do in the next hour. And just for the heck of it, I'm going to show you a little bit about, remember some of those time-dependent videos of wave functions hitting barriers. I think I'm going to be able to do one more for you next week or the week after, a really cool one. I'm going to show you a little bit about how I do those, how I make those. And I don't know that I'd have that on a test, but I kind of have to bite my tongue. It's a little bit of math. The reason I want to show you that is because I want to show you what the real Schrodinger equation is. You see, I've actually not been showing you the real Schrodinger equation. I've been showing you a simplification. The second thing is that it's a little math exercise. It's not too hard. It's a bit of a math puzzle. I'll go ahead and tell you. You know how to take a derivative. Do you know how to take e to a derivative? E, exponential derivative, right? That doesn't even make sense. Derivatives are just derivatives. How can you raise something to the power of a derivative? I'm going to show you. So it's like something that you didn't even think was possible. So that'll be in the next hour. So hopefully, for one, it'll be useful because I'll have some things from the exam. And then there's a part of it that I hope you find interesting, and again, a little bit of math building skills, and you know, I'm not even going to say it because I've said it a million times about why you want to do that. All right, so, God, 2/3 the way through, right? Almost done. Okay, so let's review where we were at last time. And we're winding down quantum mechanics. In fact, this will basically be the last day you're going to see this kind of stuff. I'm pretty sure that's true. Maybe I'm going to bite my tongue on that, but I'm pretty sure this is the last day we're going to have operators going out across the board a zillion times. And what we were doing, I know that this is hard to digest. We're working on the hydrogen atom Hamiltonian. It's rather gigantic. We wrote the thing out, which is really big because of because we're in spherical coordinates, and the angular parts are really the thing that make it go 10 miles long. You have the Coulomb potential. So we removed the angular parts and simplified, algebra, and we got here to the radial equation. Okay. Now again, you would not, I don't think I can start from the 3D kinetic operator and whittle my way down here. I did it in class because I had a set of notes. I couldn't do that on an exam. Regardless, let's see. So let's start back here. Just look at what makes sense and what doesn't. Well, everything makes sense. All right, kinetic energy. As much as it now looks very unfamiliar compared to like free wave and particle in a box, I can still recognize kinetic energy, mass of the electron. Okay, then we've got this L times L plus 1, so this is the rotational energy. And then we've got Coulomb, we've got the Coulombic interaction between the electron and the proton, and that's negative, so that's energy lowering. And then it's an eigenvalue, so we've got e to the wave function. It's kind of a mathematical curiosity that you always would end up with r times the wave function. And actually in the next hour I'll show you a little bit about what you can do with that, but don't. You can just think of it just because of all the manipulations we did. And this is done to make this as easy as possible to work with. And I'm sure back in 1920-something, when Schrodinger actually solved this, it just probably was the easiest thing to be solved. Recall that we've also, that due to separability, we have angle parts and radial parts. The angle parts don't have energy in it. The eigenvalue equation for the Hamiltonian, the eigenvalue is energy. Energy got funneled into the radial one, so the angle parts contribute, and they affect the answer. But those mini Schrodinger equations did not have energy in it. The radial did, and there it is. So the radial decides energy. Now the solution we're still getting to, we're going to get to it today. We're trying to understand the various parts. But I just wanted to say one last thing to remind you that we're going to have a new quantum number, right? For angles, we have M and L. And for the radial, we're going to have its own quantum number for its, dominant Schrodinger equation. It has an N quantum number, which we now know has to do with like the rows of the periodic table. All right, so that's where this comes from. As much as it's kind of overwhelming, it's still, especially in parts, not too hard to understand. Okay, now what we're doing is, because I finally have enough time to actually start writing down what the radial wave functions are, but before I do that, I want to point out that there's motifs in the solutions that you can understand by solving this at short distances, and this is where we ended last time. If I want to say that I'm going to solve this thing at short distances, what I can do is, let's see, just look at what I did. I got rid of this, and I got rid of this. And that's because I've got, an R dependence, I've got no R dependence here. And so I just said if R is very small, that these don't contribute compared to this, which actually has a 1 over R dependence, and so 1 over a small number is a big number. Kinetic energy, you can't really just be getting rid of that. Remember, the kinetic energy operator is always the thing that's always a real pain about quantum mechanics. It always comes from the kinetic energy operator. Okay, so I got pared down to here, and then we showed that a reasonable solution is R to the L. And so what you're really seeing here is the wave functions dealing with the fact that if the electron gets close to the nucleus, it spins way too fast, right? Now, that makes sense. I mean, of all the things that actually make sense, there's that. And what this is doing is it's accounting for the fact that the electron's going to gain way too much energy if it gets close to the nucleus. So I'm going to tell you a little bit more about that today, but I just want you to understand, big picture, that's what's happening. The fact that there's an R to the L solution has to do with the fact the electron's getting way too fast when it gets to the nucleus. And it is preventing the electron from crashing into the nucleus and whatnot. It's preventing the electron from gaining infinite amounts of energy. So the reason to solve this miniature thing is that, remember, this is an approximate solution for short distances. When we write down, I'm going to write down all of the radial wave functions for n of 1, n of 2, and n of 3. And you're always going to see an R to the L in every expression. Okay, so there you go. All right, next one. Now let's do R at long distances. And then I'll actually write down the real solutions, which again, you would need a math degree, probably math PhD, to actually solve this for real. Okay, so at long distances, what I'm going to do, now I'm going to actually mark on this. Remember, I did this last time. I'm actually still reviewing. Okay, at long distances, I'm going to remind myself, what am I going to do? Okay, at long distances, I'm actually going to get rid of the Coulomb operator, because that's the electron-proton, and that's definitely a very favorable interaction if they're close together, but I'm talking about at long distances. Now, this thing is definitely, remember, this one is dominant at short distances, so the exact opposite is true at long distances, so I'm going to get rid of that. Okay, so then I've got, here, maybe, I don't know if I'll speed up time. Sometimes I decide to speed up time when I'm looking at when I'm editing, and I figure out whether you're just sitting there watching me write things, and that's just going to make you go crazy. I guess not in this case. Looks like I got through it. Okay, so at long distances, I'm going to just simplify it this way. And here's the thing that I'll have you do. I'll have questions like this on the exam, and I'm going to do an example in the next hour. And this would be a very simple derivation. You really should be able to do this. It's a bit of just a math exercise, but you're kind of used to that at this point. This is why I have them on homeworks, and you know why it's important. So what I'm babbling about is I'm going to simplify this. I'm going to simplify this for this idea that we're at long distances. The reason I'm going to do that is simplification, and it's going to get us to the answer way quicker. And of course, again, you see that answer in all the real solutions to the whole shebang up here. Okay, now again, this is something I expect you to be able to do. When it comes to simplifying this, if you asked me to simplify this, I could just guess what you mean. You see, I've got r times the wave function in derivatives. That means that I've got a product rule. So what I can do is just work on this. I don't even need to know what the wave function is, and I can just apply the product rule even without knowing necessarily what the wave function is. Okay, so that's what I'm going to try to do. Okay, so here I'm going to write this out again, and remember how I have to write mass. I have to write mass out. It's one of the most annoying things because the m quantum number is part of the angular solution. Okay, and again, I've got two functions multiplied, and I'm taking the derivative with respect to both. Okay, so let's do the first derivative. I'm still burned about that mass. Okay, so I will, this is how I do them, by the way. Everyone has their own style. I used to maybe try to do both steps in my head, but no, I just, you know what I do is I just write out one derivative. I just leave it there, and then I just don't worry about it. Now I can just do the first derivative. Okay, now on that one, what I'm going to do is I'm going to leave r alone, and I'm going to have the derivative of the wave function, and then you do the opposite. Okay, so if I leave r alone, then I take the derivative of r and I leave the other thing alone in brackets because I have a bunch of constants. Okay, and then let's do the next derivative, and I'm afraid I've run out of space. Let's see what happens. I may have to do a lot of editing if I've run out of space. I don't like that equal sign, that bothers me. Okay, now the next derivative is, let's see here, I will leave this one alone, and now I've got a double derivative with respect to r of the wave function, and then I've got a single derivative of, then I've got, yeah, I almost messed this up. So here I have two functions. So I do the derivative, I leave that one, I do the derivative of that, then I do the derivative of that, and leave that alone. So I've got the derivative of the wave function, that's the second term of this one, and then that is actually very simple, that's just the derivative of the wave function. And I barely give myself just enough room, and so what do I get? Okay, so I'll just push this up and just keep working down. So I'm just working down from here, and again I got to write all this out again. It is, let's see, what do I end up with? I end up with 2 times the derivative of the wave function, and r times the double derivative of the wave function equal to ER wave function, which nothing happened to that. Okay, so now here's the deal. If we're at long distances, let me write that down again. At long distances, long r, this has an r in it. I mean, r can be like infinity. So one of the ways, this was kind of more of a PChem 1 thing, but we weren't in PChem 1 together. I always tell people that when it comes to manipulating equations or thinking about how to deal with them properly, you can think in extremes. So if I let r go to infinity, this term isn't going to do anything compared to that one because there's an r in it, so that's infinity. So here's my point. I'm just going to wipe that out. So that's my next simplification. Make sure you put that in your notes, right? Because if you're just watching this or you're reading your notes, you're not going to know why you just wiped that out, right? I can't write out everything myself. So that's why it's going away. And in terms of in terms of what I could put on a test, I could have you do a very similar analysis. And I will show you another one of these in the next hour. Okay, so I've already noticed that I can even simplify something further. You notice that there's an R. So remember, if there's an R in front of a derivative, there's nothing you can do about it, but this is behind it. So I can eliminate it there and there. So again, make sure that you don't mess up your notes or get confused by your own notes. Okay, and then last bit. Now so double derivative. So at this point, I know that you didn't have diffie-q, and I throw a lot of these at you. And I think I even showed you how to solve this. This one I actually showed you how to solve in one of those extra hours. But you're not going to have a diffie-q more simple than this. We can't simplify this further. The double derivative of a function is equal to itself. Well, there's a minus sign, but whatever. I think we all know what the solutions there look like. Let me just go ahead and tell you that the wave function, we're just going to call it e to the minus kr. Okay, so if we plug that in, let's see, what do we get? I'm going to plug that in here, and what we're going to end up with is minus h bar squared k squared over 2m mass, sorry, I gotta spell it out, e to the minus kr equal to e times e to the minus kr, and therefore energy, of course, is equal to all this. So there you go. Let's see. I guess I could play a little game with you here. So we've solved for the energy and whatnot, and in whatever we've also got ourselves the nature of the wave function at large distances. Let's see here. So again, what we're going to see in every wave function. Let me just remind you: every wave function, the real wave functions, have an r to the l. And they also have an e to the minus something times r. Now, we've already talked about what r to the l does, but what does this do? This just kills it off. This says that the hydrogen atom wave function has to come to an end at some point, which of course it does, right? And so yeah, that's really all I have to say about that. Let's look at a little clever math trick. Let me just throw something at you, just to be kind of difficult. And that is, if I solve for k, notice this. Let's see here, what would I get? So it looks like I get an expression that's kind of familiar, right? And let's see, I would have square root, well no, just k, so let me just say k squared. I have k squared, sorry, this is awful. You know what is funny about this is, if I'm going to then, so I've just done some algebra, sorry I had to think about it for a bit, but you may notice that I messed up a minus sign, so I'm going to bring the minus sign over here and then take the square root. So now I've got k is equal to this. Now, maybe this isn't really a what's wrong question. It looks like there's something wrong. Hopefully you recognize that I've got the square root of a minus. And that would mean that, you know, I'd have to bring a minus sign out. Square root of a minus sign is the letter I. And if k has an I in it, then this is like a sine or cosine. So I know I said that was a mouthful, but you know that if the solution is e to the minus I kr, then that's basically like cosine kr. Okay, now that doesn't decay, right? That just goes on, and that's the exact opposite of what I said. I said that this is an exponential decay, but if the momentum constant, right, the k vector, wave vector, if it has an I in it, then this actually oscillates on forever. So it seems like I've got a problem here. So you can imagine why this is a good test question. Now the answer is that you have to remember that energies are negative for the hydrogen atom. Remember that last class? Energies are negative, so I've got a negative times a negative, square root of a positive is fine, right? Nothing weird. And then I've got e to the minus just a number times r, which is an exponential decay. So you kind of see where I've got a good test question there. And I know it's a little bit of a pain because you have to remember that energies are negative, but there you go. And if you miss that, if I ask that question and you miss it, it's only a few points, right? So last bit before I have to wipe out the board is, now that I've got all this rigmarole done, let me just summarize this, that the radial wave functions, we've already remember that there's a theta and a phi wave function. Those are the spherical harmonics that we did from last week. So the radial wave functions, now these are the real ones. They're going to look like this. There's a normalization, who cares? Then there's r to the L, because we just talked about that. Now there's going to be more to it. And I'm going to call that a connector. That connects short distances to long distances. And the long distances, as we just did, is going to look like an exponential decay. Okay, so last bit I want to mention is, before I have to wipe out the board, and then we'll write down the wave functions and you can see them all, is that, as I mentioned, you're going to see this in every wave function, but for the S ones, you're not going to see this. You're not going to see an R to the L. But why would you? L is 0, right? For the 1s state, 2s state, 3s state, for S states, L is 0. There's no angular momentum. R to the 0 is 1, so you just don't see anything. So be careful. R to the L is there by virtue of its not being there. And you will see it in the rest. All right. Now I'm going to have to wipe out the board, and actually I'm going to take a bit of time because I'm going to write out all the wave functions, and we're going to just kind of look at every one of them. You don't really need to write these down because it's just a mess. It's just a mess of constants. But we're going to look at each one and graph them and understand them and whatnot. So I'm going to take a bit of a break. It's going to take me a while, but you're not going to know it. So you can see why I had to take a break there and write all this absolutely hideous facts down. Let's see. So these are the actual solutions, and you have to admit they're not as bad as the Hamiltonian itself. But it's up there. So, as I mentioned, we want to find the limiting behavior that we had explored at short and long distances in all these wave functions. Now, before we get into detail about S and P and all that, I just want to point out that we had always an e to the minus r over some a. Of course, we know that e cannot have units. It is impossible for the argument of an exponential to have units. So what I'm doing is I'm just going to break down every single thing I can about these solutions. So we can't have e to the minus r by itself because that would have units of e to the minus distance, and you're not allowed to do that. So it turns out that the solution has a mess of constants in it, a, which again, yeah, mess of constants. Remember that e squared, that's actually the charge of an electron in coulombs. And when you multiply all this out and you're in SI units, you would get 0.052 times 10 to the minus 9 meters, which is 0.052 nanometers. But old-timey chemists use angstroms because bonds are about 1 angstrom. And so this is about half a bond. But that kind of makes sense. A hydrogen atom, an atom would be about half the length of a bond, right? Of course, it's a small atom. Okay, anyway, so this makes sense. And so here's our exponential decay. And we see that it decays in every single wave function, all the wave functions I've drawn. Okay, so just wanted to point that out. Now, maybe I kind of jumped at the end. Let's go back and let's take it a little bit easier and let's look at the names of these things. Okay, so the principal quantum number is when Schrödinger and some mathematician, I think he had to actually get help with from another mathematician to solve that. They found, an infinite number of solutions, and the solutions you could keep track of them with a quantum number that went 1, 2, 3, 4, 5, 6, and that was the n quantum number, right? So now remember that there's a dependency upon L, the angular momentum, in n. We talked about that last time. So if the principal quantum number is 1, which is the ground state, then you cannot find the solution for anything unless L is 0. So that's kind of how it works. So if you look at that giant mess of an equation I wrote before, and you plug in an L of 0, and you're looking for the n equals 1 solution, you'll find it. But if you use any other L, and you look for an n of 1 solution, you're not. It's just, there isn't one. So they don't exist. So the ground state of a hydrogen atom is the 1s. Now, hydrogen will generally be in the ground state, but it can be put into its excited states. All the remaining states are excited states, right? And there's technically an infinite number. Now, one of the things that, this slays me, every year I ask about these various states, and people say, the 1s state is real, and none of those others exist. And every year I say what I'm about to say. This is the ground state, and these are excited states. They exist as long as you put the hydrogen atom in those states. What you can do is make hydrogen, atomic hydrogen, which we do all the time in gas chambers and those giant spectrometers, and you can shine light on them to get, or put a lightning bolt through it, put a discharge of electricity. You can do all kinds of things. You can just heat them up unbelievably hot, and they can go into excited states. So those excited states are real, they're just not the ground state. Okay, now when it comes to the, so the last thing to note is that that R to the L, the R to the 0, which is 1, is present, but you can't tell because 1 is 1. Okay, so the 1s state makes sense. Remember that you always just represent that like this, right? And the S state, of course, we looked at the wave functions before, that's just a sphere, right? Okay, now the 2s state is an excited state, and again, when it comes to solving this, when you're looking for solutions for the second quantum number, then the mathematicians can say, I can find a solution if L is 0 and if L is 1. I can find one solution here, and I can find three solutions if L is 1. 1 if L is 0, 3 if L is 1. And that's because these are the P states, right? L is 0 is S, L of 1 is P. The mathematicians can find 3 states because those are Px, Py, and Pz orbitals. So anyway, so that makes sense. Let's see here. Okay, tell you what, let's look at the 1s to 2s. Notice that the major difference is that we've got, where's our R to the L? Let's see. No, never mind. Let's see, I'm sorry, I see that in the 2p, right? R to the L, R to the 1 is right there. Okay, so why is this messier? Why is this messier, right? This is designed to introduce a node. So if we're going to have a 1s and a 2s state, and they're both like round, they have to be different in some way. And the 2s state has to be higher in energy. It's an excited state. How do you make it an excited state? Well, what happens is you just have a more complex radial wave function, and when you start adding polynomials, you can introduce nodes, right? It's like, x squared plus x plus constant, right? You can have crossings, you can have 0 crossings, right? Now, to emphasize that, let's look at the 3s. The 3s state, we see even a more complicated polynomial. So now we see an r squared r and a constant. So that can have a function, a square of a function can have 2 zeros, right? That's like the quadratic equation. So this can have 2 nodes. So no nodes, 1 node, 2 nodes. So that's how the S states differ from each other. They pick up nodes, and that increases their energy, but they have to have an increase in energy because the 2s is an excited state, and the 3s is even a further excited state. The only way to have extra energy is to pick up nodes, which it has to do with kinetic energy. Okay, now I mentioned, so if n is 2, the mathematicians can find 3 L equals 1 states. We know those are Px, Py, and Pz. We see the R to the L behavior. So let's look at, I didn't write out 3p, because I could be writing things all day. This is already kind of horrible. Where's R to the L? Well, L is 2, so I see an R squared there, so there's R to the L. And there's no nodes, but why would there be? I think there would be nodes, no nodes here, right? But there would be if I was looking at a 4D state. 4D state because that would have to pick up kinetic energy compared to the 3D. So, yeah, that's really about all I have to say about these. There's a couple of other little minuscule bits of information, and then we're going to start plotting these things, and I'm going to basically repeat everything I just said, and hopefully between just pointing them out in an equation and then pointing them out in a graph, it'll connect. And yes, these will be on an exam. On the exam, I'll have graphs. I'm not going to have you just stare at these and figure them out, right? That's ridiculous. No matter how mathematical you are, that's kind of ridiculous. I just want to make sure that everything, present things multiple different ways. Okay, there's a couple of little factoids that I wanted to go over before we started graphing things, and that is that there's some old-timey language. So let me write that, old language, that you actually will see this quite commonly. It's German. So remember that N tells us about, the electronic structure of the hydrogen atom. N of 1 is the ground state, and every other N is an excited state. But it also tells us about the rows of the periodic table. Now that's because when you have more electrons, when you go from hydrogen to helium, you fill up the 1s state. It's one orbital. It can only hold 2 electrons, spin up and spin down. So then when you go down, when you add one more electron and you go down a row, then the ground state, the frontier valence state, the ones that participate in bonding, and that's for lithium, and the first thing with 3 electrons, right? Its electron is in the 2s state. So that thing is going to be bonding by the 2s state because the 1s state is filled. And so generally we think of those as fairly inert. And then when we get to the p block, then we have so many electrons that the 1s and 2s are filled. And so the valence electrons are all in the p state, the first p state that's allowed, which is the 2p state. So that's why for carbon and nitrogen and whatnot, you're always looking at how the p orbitals bond. So the n quantum number has kind of double duty. It tells us about hydrogen because that's what it was designed to do, but it also tells us a lot about how the periodic table is structured. And again, the reason is because as you look at other types of atoms and you add electrons, you fill up orbitals. And we know that filled orbitals don't really participate in bonding. So that's why n ends up being kind of hideously important. Okay, old language, N of 1. Okay, so I swear to God, I see this all the time, so I gotta tell you about it. This is often called the K shell. And N of 2, so again, we could be talking about hydrogen excited state, or we could be talking about the electronic structure of heavier atoms. N of 2 is called the L shell, 3 is the M shell, 4 is the N shell. Now, where you hear about these is in X-ray technology. You people want to be medical and this and that. You are going to be dealing with X-rays because we use X-rays to look at people. You may see this type of terminology. Now, you also may see it used to describe radioactive processes. Radioactive processes are also used in medicine for imaging. We also do like biochemical titrations with radioactive elements. So again, I just want to point out to you, X-rays happen, radio labeling, like for PET scans, you heard about those? The processes involve, electrons and atoms, and sometimes you will see them described as, oh, that's a K-shell process. This X-ray or this radio label is a K type of label, and what they're talking about is something that's occurring with the 1s state. So you may see this, and this is what it's talking about. Okay. Now, we all know that, and I've already said this, L 0, 1, 2, 3, S, P, D, and of course 3 is F. Remember that when we're talking about the F block, that's the weird part that hangs at the bottom of the periodic table. That's when we're talking about uranium and plutonium, and I'm sure in a physics class they spend a lot of time on that because they're all about the nukes, but we don't really do too much chemical work with plutonium. If you did, you would really be in jail pretty quick. Okay, last bit before we start doing a bunch of graphs is, sorry folks, major camera glitch there. I'm not even sure where I was at, so I'm sorry if this is a little funky here. All right, what I was talking about was some last little facts about, interesting facts that we can gather from these wave functions here. And what's really interesting about, I've been mentioning the rows of the periodic table, and we all know that the periodic table comes to an end at some point. Every now and then, well, it's been a long time, but in the last 20 years, there's been like 4 or 5 elements discovered, and probably there won't be any more elements discovered. You've probably heard that when they make these in like super colliders, that the elements don't live very long. They have short half-lives, right? I think you've heard that before. We're going to cover that in kinetics. All right, it turns out that we can use these wave functions to understand why the periodic table is only so big. Okay, now to do that, and to remind you of what you can do with wave functions, notice that I'm writing an expectation value. Okay, how do we do expectation values? Now you better know how to do expectation values in general, but you know that there's always some nuances, like what are the limits? Well, it would be 0 to infinity. There's no such thing as a negative r. R is the net distance, right? There's no negative net distances. Now, of course, we would, if we're looking at the wave function, we need, we might have complex components, not in the radial, but in the angular parts. That's possible. But we're just doing the radial, but still, though, I'm gonna write down the absolute value squared like normal. Don't forget that there's a Jacobian, 4 pi r squared. Now recall that we're integrating over volume, dx, dy, dz, except that we're actually using r, theta, and phi. There's a Jacobian with that transformation, and that's where we get a 4 pi r squared. Okay, then there's the change in r. And it turns out that, hopefully, you've noticed I've made a mistake. Because I'm going to put this on the test or something like this, right? I have to have an r in between, right? If I didn't include that r, then I would have integrated out to 1, right? I'm just integrating the wave function squared times the Jacobian, and that's just 1. It's probably somewhere. So I have to include an r, so I'm really doing 4 pi r cubed. Okay, irregardless. It turns out that these wave functions I've written here, these are for hydrogen. Now, if I was doing helium, helium plus, all right, so it has 1 electron just like hydrogen. So let's make it easy. The difference is that it has a greater nuclear charge. It has 2 protons, hydrogen has 1. Now what that does is it would affect the wave function. I haven't written it down, but the nuclear charge, Z, would appear in the wave function. And again, just to make your life easier, I haven't included that. Now regardless, let's say we did, you can just Google this stuff. You would find that the expectation value for where is the 1s electron scales as 1 over the mass of the nucleus. So as the nucleus gets heavier, the location of the electron gets closer and closer to the nucleus. So what's happening is, the 1s is the first, here's the nucleus, and the next thing is the 1s electron. It's always right there next to the nucleus. All the other electrons are further out. They're kind of pushing it in. So as the nucleus gets a higher Z, as it gains mass, the Coulombic interaction is stronger and stronger, and so the 1s is going to shrink and shrink and shrink. The nucleus is getting bigger, the 1s electron is getting closer. Well, see, there's a limit. Eventually, the electron can crash into the nucleus, and Coulomb's law says that's like 1 over r amount of energy gets released, and that would destroy the universe. Okay, to prevent that from happening, the nucleus just falls apart. So there's like a nuclear fission event. So when you try to make these super heavy atoms, there's a limit, because if this thing is basically touching the nucleus, the atom is just going to fall apart before that happens. So again, this is another little interesting factoid that we can learn from these wave functions why can we only find so many elements? Why does there seem to be a limit to how heavy an element we can make and how far the periodic table goes? Personally, I think we're kind of at the end of what we can make in terms of atoms. Okay, next bit. Let's still explore these wave functions further. I want to graph them. I mentioned I was going to graph them. And, you know, I've pointed towards R's and polynomials and all that, and I know that may be unsatisfying for most of you. Maybe some of you, that gets in your head. That's great. That's why I said it. Let's look at graphs. That's a little bit better. And if I have things on the test, which I will have things on the test, I'll have graphs, and I'll ask you to interpret the graphs, interpret these radial wave functions. All right, so I'm going to do that as a function of L. Okay, so we're going to start with the L of 0, the S states. And let's see, what do I want to tell you about that? Okay, now if I'm going to talk about the whole hydrogen atom wave function, this is a good point to remind you, I know I've already said it, but I want to remind you that there are theta and phi wave functions still. But for the L of 0, remember from last week, for L of 0, the S states, these are just constants. Now the constants are only designed to do this. Now you may recall that, again, I'm integrating wave functions. 0 to pi, of course, is for theta. Theta does this. It only goes, you know, halfway. So 0 to pi for theta. 0 to 2 pi for phi. Phi is this one, so it goes all the way around. That's 0 to 2 pi. Okay, as I was just babbling before, we're going to have our wave functions, the absolute value squared. And we definitely want to make sure that we use the proper terminology here, because remember that the phi wave function is like e to the I m phi, so it's complex. When it's complex, you better make sure that you use the right mathematical, you know, absolute value when you have a complex function. So next bit, Jacobian. This thing has a Jacobian too. Right, remember, we're doing a volume integral in x, y, and z, except we transform to r, theta, and phi, and we have to pick up a Jacobian, and that's our angle part. Phi doesn't seem to do anything, but there you go. Now, recall again that for the L of 0, this is utterly boring. It's just a number designed to make that go to 1. So that's all it does. It's just super stupid. It is what it is. Now that means that for the L of 0 wave functions, it's way more interesting to look at the radial wave functions. The theta and phi's, again, there is no wave function. Right? That's why the S states are just round. Let's see here. Okay, now, so what we're going to do now is graph those things I had before, and hopefully all the things I was, you know, I know it's not so smart of me, and I know I do it all the time. I point at cosines and r's and say, oh yeah, you know what that means, right? So let's graph it. I think that would be a little bit better. And let's graph the, okay, so let's say that you're at the test and you see a graph and you're asked to identify it, right? So let's say that you see that. Okay. Now I would know immediately, without looking at those equations, and if you need those, all those equations, if you need them, they're on the test. But I would know immediately that this is the 1s state. Now the way I know that is mostly the fact, a little arrow there, mostly the fact that there's no nodes, 0 nodes. Nodes signify excited state. If I have one node, I bet it's a 2s. If I have 2 nodes, it's going to be a 3s state. That's how they distinguish themselves. The next thing I notice is that the wave function is finite at r of 0. Now that's fancy math speak for saying it's not 0. To say that something is finite is to say that it is not 0. So the wave function is not 0 at r of 0, and again, that's a sign of an S state. Okay, let's do 2s and 3s, and hopefully you can kind of guess what this looks like. Maybe I'm doing some computer graphics, but these get like really flat. It's hard to draw these on the same scale. It's kind of messed up how this works, but okay, so the 2s is like this, It goes a little further than the 1s, but that kind of makes sense, right? In this excited state, so the electron gets like a little further away from the nucleus, so that makes sense. And we picked up a single node right there. So that makes sense. Now the 3s state, it's even a little bit worse. It's again, these like look really flat compared to the 1s state. So that looks like this. So there's one node, then you get a second node, but then of course it has to decay off to 0. So there you go. There's the two nodes. And let me label these. So that is 2s, and this is 3s. So what you're looking for in this type of behavior is you're looking for nodes. You're looking for nodes to tell you whether you're talking about 1s, 2s, or 3s, and you're looking to see whether they're finite. Now hint, the p and d states are not finite. They are 0 at r of 0. Just in a moment, just in a moment. That's why I'm talking about this so much. Okay, actually, let me continue on talking about how they're finite at r of 0. Turns out that that's a funky thing. Now, remember how I just babbled on about the world exploding due to heavy transuranium elements? Because the electron would smash into the nucleus, that can't happen because the world would come to an end. Okay, now a strict interpretation of a wave function being finite at r of 0. At r of 0, that's where the nucleus is by definition. So if the wave function of these electrons is finite at r of 0, it implies that there's some probability for them to be there. If they are there, they're hitting the nucleus. If they're hitting the nucleus, an infinite amount of energy is being released. So this is a bit of a problem. How can these be the right solutions? We think of the wave functions of the Hamiltonian as representing reality, yet it seems like we have a bit of a problem. All right, the solution actually still comes back to here. Our equation for average distance is the Jacobian. The Jacobian, and remember that what that does is it represents volume. It's a volume element. Okay, so let's think about this. So probability is, of course, proportional to the wave function squared, but it's also got to have a volume element. So it's proportional to the wave function squared times r squared. Okay, so now if I plot that, wave function squared r squared versus r, for any of these states, it's actually going to look like this. Right? The multiplying factor of r squared means that it actually is not 0, 0. It's important to label your axes. It says that despite the wave function being finite, what it really says, I mean, it says like, okay, it says what this graph says, but let me put this in ways that a high school student would understand. Since this is basically the volume element, and the wave function squared times the volume element is 0, what it's physically representing is that the electron can't find the nucleus. The nucleus is technically modeled as a single point, and in geometry, a single point has no volume. So the electron can get arbitrarily close to it, but it can never find the nucleus because the nucleus basically has no volume. And remember that this is like Rutherford's description of the atom that you read about in high school or freshman chemistry, how the atom is almost entirely, has almost no volume, how the nucleus is such a really small amount of the volume of an atom. Well, there you go, you're seeing that behavior. So while the wave function is finite at r of 0, it actually can't find the nucleus and therefore hit it and therefore destroy the universe. So the universe is still intact. It's still intact as of this lecture. Okay, let's see, now I'm going to need to wipe out the board. Okay, you know what, I'm going to leave those wave functions up there. We're almost done. So now let's look at p orbits. So L of 1 and 2. All right, remember p and d orbitals, and I'm not going to worry about f states or whatnot. Actually, I might have a question on your homework about f states. It's kind of busy work. Let's see now, what do those wave functions look like? Now, we've already talked about the theta and phi. When I mentioned those before for the S state and how they were constant, I just wanted you to remember that there are still theta and phi wave wave functions, right? The total wave function is the r times the theta times the phi. Right. Okay, so the thing about these things, let's do 2p. I'll do the 2p. That's the first excited state of the hydrogen atom. Let me draw that. And again, you can look at those functions and use some software to graph it yourself, or you can just trust me, it's what I draw here. Okay, it looks like that. I didn't do that very well, did I? There we go. Okay, so that's what it looks like. Now, okay, exam time. I see this thing and I'm asked, identify it. Okay, how do I know it's a 2p? All right, number one, it is not finite at r of 0. It is 0 at r of 0. Now that means it is not an S state, it's either a P or a D state. Now, next thing, no nodes, right? So I don't see any crossings of 0. So that means that this is very likely a 2p state. In that contrast, let's say, let me draw a 3D state. That would look something like this. Okay, so that's a 3p state. There you go. And you know that because it has a single node. Okay, so of course a 4p state would have 2 nodes and on and on and on. And whenever I make nice graphs of these, I have to like spend a lot of time on Wikipedia and Google trying to find a website that describes all these wave functions correctly. There's oddly sites out there that write the functions down incorrectly. So there you go, there's not much to say about that. Now what you're seeing here in terms of the wave function not being finite at r of 0, that is actually due to the r to the L component that I've been talking about so much from the last lecture up to this one. That's the r to the L part of those higher angular momentum wave functions. That's what's doing that. So not only does that also help the electron not touch the nucleus, although we've seen that that's not really a problem no matter what that does is in these states are rotating. So this idea of the electron going faster and faster as it gets closer to the nucleus, that's not true for a 1s or a 2s or a 3s state because it's not rotating, right? And I know that's so weird because those wave functions are round, but they're not rotating. And I don't understand it other than just what I've done here. I don't understand it up here, but there you go. Okay, for P and D states, they are rotating. And that means that as they get closer to the nucleus, they are spinning it faster and faster and faster. If they're allowed to get like real close to the nucleus, they would be spinning so fast they would have infinite amount of energy. So you're not allowed to do that. And this R to the L term prevents the wave function, keeps the wave function down, keeps the electron from getting too close to the nucleus, keeps the electron from spinning too fast, keeps the electron from gaining infinite amount of energy from spinning too fast. So that's how all this works.